My name is Tiantu. My topic is plane segmentation and depth prediction. In everyday life, understanding the scene around us is very important. Human vision is remarkable in understanding high-level scene structures like floors and walls by perceiving major surfaces for an outdoor building or indoor furniture. Machine vision, on the other hand, is much weaker than human vision, but it is the foundation of a wide range of applications in the domain of robotics, augmented reality, and autonomous driving. For the AR case, if we want to place an AR object, we need to first figure out the surface to place that object, and then how far the surface is from our camera to adjust the AR object size. 10 years ago, the traditional computer vision community had proposed the bottom-up approach, which studies the local colors, the textures, and edge cues for each pixel in the image to segment the planes of the real scene. With the development of deep neural networks in the past few years, people proposed top-down approach that trains an end-to-end deep neural network. So why does the bottom-up approach work poorly? Because primitives or features may not be reliably detected due to the poorly textured or specular surfaces. And also, there will be a large number of irrelevant features or outliers due to non-planar objects. So I picked 3 state-of-the-art papers working on this problem. RoomNet is from ECE570 that proposes the deep neural network to estimate the room layout by detecting and connecting the room key points like corners. PlaneNet from CVPR18 and Yang from ECE570 both trains an end-to-end deep neural network to output the plane segmentation and the plane depth in conjunction. PlaneNet requires the manual labeling of plane segmentation results, but Yang studies the depth difference threshold to automatically segment different planes directly from the depth map provided by the dataset. So I propose an extension based on Yang. Yang's architecture is an encoder-decoder architecture with 2 output branches that predict the plane depth and plane segmentation in conjunction. Specifically, the encoder takes the whole image as the input and produces high-level feature maps via convolutional neural network. The decoder then gradually upsamples the feature maps via deep convolutional layers to make final predictions, taking into account also the features from different encoder layers. The plane parameter prediction branch shares the same high-level feature maps with the segmentation branch. The multi-scale side prediction further allows the network to be trained with deeper supervision. I extend Yang by applying alternative architectures like similar to VGG and ResNet 50 besides their own implementation of DispNet architecture. And the loss function is defined on the slides. So Q represents the 3D points derived from the 2D pixel coordinates, and S represents the probability that this pixel belongs to plane J. And N transpose Q equals 1 if and only if Q is on that plane. So evaluation is in 2 folds. For quantitative results, the plane depth prediction is evaluated. Besides relative absolute error, my 2 own implementations outperforms Yang on relative squared error, the root mean squared error, and log root mean squared error with lower errors. However, it pays the actual cost in time while inferencing those images. Yang is still the best, and the inference speed is 0.1 seconds per image, which means that for a 10 FPS camera, it can do it in real time. Qualitatively, it is evaluated by the plane segmentation result, and both of my 2 alternatives are competitive to Yang's implementation. In conclusion, besides Yang, trying alternative well-known architectures like VGG and ResNet 50 could reduce the plane prediction error with the cost of more computation. The plane segmentation of all alternatives derives the competitive results compared to Yang. To support real-time applications like autonomous driving, the inference latency is also very important, so that the designers should also explore the trade-off space between the prediction error and latency.